Welcome to this section of solving the regression problem in machine learning language. In this section, we'll start with a brief overview of the functionality in SciPy to tackle optimization problems. Then we'll start writing our own implementation of the gradient descent algorithm, helpful to solve some optimization problems in machine learning. Specifically, you'll become acquainted with the following topics: overview of optimization and the gradient descent method, gradient descent method implemented via NumPy and examples, comparing it with SciPy functions for optimization, linear regression problem and its solution via gradient descent, solving nonlinear regression problems via gradient descent, and some thoughts for improvements. Moving on to the first video of the section, starts with an overview of optimization and the gradient descent method. Specifically in this video, we're going to have fun recalling ideas about optimization. Then we'll set the theoretical basis, the basis of the gradient descent method, which we'll program in the next video. We'll be providing an overview of optimization and theoretical digression about the gradient descent method. In general terms, optimization deals with the optimal use of resources, subject to constraint conditions. Mathematical terms, optimization problems are posed in terms of finding the local or global minimum or maximum of an objective or function subject to a set of specified conditions. An example could be finding the greatest volume one could subject to the amount of material available to build a container, or in financial investment activities, given a set of stocks on which one would like to invest. How much money one has should be allocated to each stock, minimizing the amount of risk, while maximizing the return we could obtain. An optimization problem could be discrete or continuous, linear and nonlinear, and linear and nonlinear, from which a special case is termed quadratic programming. From calculus, these types of problems ask for finding the zeros of the derivative of a continuous well-behaved function. Then looking at the sign of the second derivative of the function to find out whether a minimum or maximum has been found. Let's mention that the SciPy library has many methods implemented for dealing with optimization problems. A detailed listing is available at this link. As you can see browsing the documentation, there are functions for local optimization, linear programming, and many other related root-finding functions, including a section for the Rosenbrock function, which you can read at this link, containing the function, its derivative, and the Hessian matrix, about which you can read at this link. This function is used as a benchmark for any optimization algorithm. A particular optimization method, and very popular in machine learning, is gradient descent or steepest descent. It's a first-order iterative optimization algorithm that finds a local minimum of a function by taking steps proportional to the negative of the numerical approximate gradient of the function at the current point. We have a set of m set of values, and we want to fit them to a lineal model defined by the function h, which in machine learning terminology is called the hypothesis that approximates the true unknown function. From where the m data set points come from. Notice that we've chosen to represent each variable or feature in columns vectors. xi, the x0 vector, is introduced for convenience and its component are all ones. For each data point, the idea is to get the hypothesis h close to each value of the dependent variable yi. One way to do that is by minimizing the squared error or cost function defined here. The gradient descent algorithm is defined by finding the set of values of the zeros that minimize the squared error or cost function. This is done by starting with a set of initial values for the zeros and update them according to the equation shown here, where each initial theta is updated by taking from that initial value the derivative or gradient of the cost function, respective of 0 being updated times a parameter called the learning rate. The iterative process is repeated until the change in the zeros reach a tolerance level. Intuitively, this iterative process for updating the zeros will converge when the gradient or the derivative of the squared error cost function. When the gradient or the derivative of the squared error cost function reaches a local minimum where the derivative of j will be 0, and the zeros does not change anymore, we can see how the derivative of the cost function is found. I is found. Cost function j is found. A more convenient form of these derivatives can be found if one represents the variables or features x in columns in a matrix. Each column contains m rows, which are the number of observations in the dataset. Using this representation and with a deep breath, we can get the matrix form shown here. I encourage you to develop the product. It involves and rearranges the terms to the sum expression given above. Inspecting this last expression, we can get the compact form for the derivatives of the cost function j shown here. This is the expression we're going to use in the next video to program the gradient descent algorithm. You can read more about these features in these links. In this video, we refresh the ideas on optimization and how the gradient descent algorithm is defined in mathematical terms.